National Accelerator Facility is a laboratory for basic nuclear physics research operated by the U.S. Department of Energy. At Jefferson Lab, scientists can advance our understanding of matter itself by probing quarks and gluons in the atom's nucleus with beams of electrons from the superconducting accelerator. Jefferson Lab has an educational mission as well. The Jefferson Lab Science Series features scientists and engineers who are gifted in making their work not only informative but fun. The Science Series is held once a month in the Jefferson Lab Auditorium. The presentation is live, spontaneous, and unrehearsed.
Good evening, and welcome to Jefferson Lab's Science Series. My name is Scott Price. I'm a nuclear physicist here at Jefferson Lab. I work on the polarized electron source and electron polarimetry methods for the injector group. This evening, I have the pleasure of introducing tonight's speakers, Dr. Tarek Sammakia and Dr. Gordon Yee, chemistry professors from the University of Colorado. Dr. Sammakia, who specializes in organic chemistry, received his PhD from Yale in 1988. Dr. Yee specializes in materials chemistry and received his PhD from Stanford in 1990. They usually team up once a year to give this presentation. They have graciously accepted and agreed to take their show on the road for our science series. Join me in welcoming the presenters of Polymers, Foams, and Gels, Dr. Sammakia and Dr. Yee.
Thank you and good evening.
Welcome to our show. This is Gordon Yee and Tarek Sammakia. Is Scott mentioned, we're from the University of Colorado Boulder. We normally do this show at CU about once a year, as Scott mentioned, and this is the first time we've ever taken it on the road, so hopefully everything is going to survive intact. What we typically like to do is get the show started with a bang. The show is about polymers, foams, and gels, but we'd like to sort of do some things that are a little bit different and show you some properties that are unusual about these materials, and just have a little bit of fun every now and then. So what we generally do is just start the show off with a bang and explode some hydrogen balloons. Now, I'm not sure what this illustrates, but it's kind of neat.
Well, rubber's a polymer.
Rubber's a polymer, that's what it illustrates.
Cover your ears.
Oh, you should also cover your ears. It's pretty loud. If you have any little kids, make sure they cover their ears as well, because it's a little bit loud. If we could dim the lights down a little bit as well. Oh, one more. What we want to do is tell you a little bit about polymers, what polymers are, how they're made, and then go from there and polymerize the audience to sort of describe exactly what a polymer is by polymerizing the audience, give you a real-life feel for what's going on. And Gordon's going to is going to describe to you exactly what a polymer is made of, and we'll go from there.
Okay, first thing. They told us that we should try to teach you a little something. So here's the first thing we're going to try to teach you. First of all, a polymer is a large molecule consisting of repeating units connected together like the cars of a train. And we made a little picture here to show you what we're talking about. A polymer consists of something called a monomer. And the monomer are these little Pac-Man type things here. And we're going to turn you all into monomers in a moment. And then something happens which turns the monomers into polymers and links them up like the cars of a train. And to give you some example of some monomers and their corresponding polymers, we've got polyethylene. I don't think we're going to show you any polyethylene tonight, but saran wrap is polyethylene. Polystyrene we're definitely going to show you tonight. Polyester or polyethylene terephthalate are 2-liter bottles. We're going to show you that tonight. Nylon we're certainly going to show you tonight, and that's made up of amino acids, as are proteins like your hair. And finally, something we're not going to show you tonight, but that you all have, is DNA, which consists of nucleic acids.
Now, one thing we like to do is sort of demonstrate the useful properties of polymers, and we like to get a lot of volunteers. So is there somebody who's willing to volunteer, somebody who's relatively brave? I'd like to go to the back of the audience and move it around a bit. Okay. There you go. All right. So one useful thing about polymers is that they're very lightweight. They're not very heavy. Please, what's your name?
Frank.
Frank, could you stand up, Frank? So polymers are very lightweight. They're not very heavy, and they have interesting properties. And one useful property, I want you to do what I do, Frank, okay? Hold your bottle like this, and then... Oh. There you go.
Harder.
So one useful... Harder.
No.
So one useful thing about polymers is that they're soft, they're durable, they're light, they bend, they don't shatter when you hit them on your head. Thank you, Frank. Have a seat. And so it's a much more useful property than glass if you're worried about breaking something, or if you're worried about breaking something, weight in shipping or whatever.
Okay, can I get a couple more? How about you two up here? Come on up. All right, this is going to be a test of strength. Come on up. Your names? Your name? Lindsay. Lindsay and Maggie. Here you go. Megan, I'm sorry. All right, get ready. I want you to tear your envelope exactly the same time I do. Okay, ready? Get set, go. Oh, come on, come on. All right. What Lindsay and Megan here are not exactly what I have. I have a typical paper envelope. You can keep those and you can sit down now. They have what is known as a Tyvek envelope. And Tyvek is polypropylene, which is very closely related to the top polymer up there. And obviously, if you make an envelope that you can't tear because it's made out of a polymer, then it gets through the mail, and whatever you have on the inside makes it intact.
Well, one of the good things about the show is we get to give away lots of things. Anybody want an envelope? There you go. How about a 2-liter or a bottle? There you go. It's not quite 2-liter. One other thing about polymers is that they tend to change their properties with temperature. So here we have a typical rubber ball. It tends to bounce. And this is a racket ball or a hand ball, and it's at room temperature. It normally bounces and is flexible. And where are the gloves, Gordon?
Right.
There you go. Go ahead. And what we have here is some liquid nitrogen, which is very cold. And what we've done is we've taken one of these balls and we've immersed it in the liquid nitrogen. So now the ball is extremely cold. And we'll compare the properties of the ball. Let's get some goggles on also. Good idea. Thank you. Gordon. No, you're fine.
Ready?
Yeah, sure.
Oh, can you squat down? Can you squat down?
Good. Back off.
Thanks. Okay, so this ball is extremely cold, and let's see what happens. Okay, I threw that a little too hard.
Did it really get it?
Let's not do that anymore.
No, of course not. So the point is, when polymers are very cold, they get brittle and they tend to shatter. And they behave very differently with different temperatures. It didn't really hit you in the eye, did it? Not very fun. Okay, so anybody want to, I guess, no, we're not going to give away the rubber ball. So can people name other things that are made of polymers? Can you sort of, what can you think of that's made of a polymer? What do you say? Yeah, polyethylene bag. How about underwear? So here we have some underwear. This is yours? And it's made of a polymer. It's made of cotton. Cotton is a perfectly good polymer made of a number of repeating sugar units. And we get to give away underwear. Anybody? There you go. Something else that's made of a polymer is nylon. And nylon is one of the first polymers that really sort of changed our lives. We didn't have to go to silk anymore to get these sorts of stockings. We could go to nylon. I kind of like these. I think I'm going to keep them. Also made of a polymer, and I should give this back. Thank you very much, ma'am. And of course, we wouldn't be, well, anybody want these? Not you, sir. Anybody? I think I'll keep these. So as you can see, polymers are around you all day. You wear them, you sit in them, you do all kinds of things, and polymers are very useful materials.
Okay, next thing we're going to do to give you some idea of exactly how something gets polymerized is we're going to polymerize all of you. Okay? So if you could please all just stand up. Okay. We're going to grab me 4 people.
Can we use you for volunteer? Okay. How about you two? How about...
Okay.
You
The
two,
rules are,
and you as well.
rule 1 is do nothing until someone takes one of your hands.
Let's explain what we're doing. You guys are all monomers in the audience, and monomers are small molecules. And when you form a monomer, like Gordon said, when you form a polymer, you take a monomer and you link them all together. And you link them through a chemical bond. And what we're going to do is we're going to simulate a chemical bond by holding hands. Okay? Now the rules are, as Gordon was saying,
Do nothing until someone takes a hold of one of your hands. But then once someone takes one of your hands, find someone else's hand and grab that.
and the chemical analogy to what's happening is a bond is being formed. And the way polymers are formed is there's something known as an initiator that begins a chemical reaction. And once the initiator reacts with the monomer finds another monomer and forms a chemical bond. But the bond can't occur until the initiator reacts with the original monomer.
So in other words, you all can't do anything right now, right? Because nobody can grab anyone else's hand, because you can't grab someone else's hand until somebody grabs one of your hands. So you're all perfectly stable as monomers. Okay? And now what we're going to do is we're going to add something to the pot, and that something we're going to add to the pot is initiator. And these are our 4 initiators right here. Okay? And we're going to add initiators to the pot. So turn around. I'll give you an initiator sign. Okay? Oops.
I don't know, they're tagged.
No, that won't come right.
Oh, you tied them.
Let go.
Let's just cut it. There we go.
I got it.
You got it?
Why don't you finish? I'll retie it.
All right.
Hold that one up. You need this one.
Okay. Okay, so these folks are all initiators. There you go.
All right, thanks, Scott, for being such a good sport. There you go. You're a regular initiator now. All right, now initiators, just take your, okay, you can turn around now. You really are initiators, and go out.
Go out and just find somebody's hand, and then once you hold somebody's hand, they can then hold somebody else's hand,
Okay.
and then we'll polymerize the entire
So a couple
object.
of you should go up towards, a couple of the initiators should
Go
go
ahead.
up towards the back, and a couple stay up towards the
Go in
front.
the back and
Okay,
grab
go.
something.
Go off, be free, initiate.
Once you go further back there, so now you
Okay,
can.
and remember, once somebody grabs your hand, you find someone else's hand to grab. So get going.
So do it quickly
One
so
hand.
we can.
There. Here you go.
Go ahead, you grab.
Go.
Then you can.
You grab that.
And then go ahead and
You
grab
turn
your
there.
hand over
You
there.
turn around. Good. Keep going faster. Come on.
So now one thing I want you to think about is that if the room is completely linked to each other like we're going to be doing here in a minute, the properties of that molecule will be very different from the properties of a molecule by itself. So the properties of the monomers are not the same as the properties of the polymer because the polymer is completely linked, and if one person moves, everybody has to move together.
Okay.
And
Are we
let's
making
cheat a little bit
chains?
here. It's okay.
Don't worry about it. That happens.
Okay, so now if everybody raises their hand, we'll see hopefully the whole room is polymerized.
Is the whole room polymerized?
I suggest you cheat and grab somebody's hand.
Okay, so you
That's
get
what we
the
do.
idea, though, that eventually everybody would be holding hands with somebody else.
You want to skip the cross-looking, or you want to do the cross-looking?
Yeah, okay.
Skip it?
Okay.
You get to keep those, that's right. Thanks a lot for your help.
MMA, right?
Yeah. Okay,
What?
so now, PMA. So now what we'd like to do is actually make a polymer, and the polymer we want to make is called polymethyl methacrylate. Now, when we do this show at University of Colorado, we have a lot of educators in the audience, And we usually ask for a $20 bill, but is anybody here not an educator? Could spare $20? Will I get it back? Sure. Just kidding. No, really, we need a $20 bill. You get it back. Don't worry about it. We won't pick on the same person twice. Okay, good. Thanks a lot. That's for dinner. So one of the things we do, thank you. So one of the things we do is we keep the $20 bill. What we do is the following. PMMA, where's the AIP? Oh, here it is. Polymethyl methacrylate is a monomer. And this is a monomer that polymerizes to form plexiglass and similar sorts of things. And what we're going to do is we're going to polymerize it. And we're going to put this $20 bill in here, and I'll give it back to you. Is that all right?
Yeah, it only works with a 20. Okay, again, what we're basically making, or what we are making exactly, is plexiglass. We're going to make some plexiglass. In this case, methyl methacrylate is the monomer, and the initiator is something that some of you who've hit puberty are familiar with. It's benzoyl peroxide. And what is benzoyl peroxide? It's zit medicine, exactly. It turns out zit medicine has the property that it will make this reaction get started in exactly the same way we tried to describe, where a molecule doesn't do anything until it reacts with one hand, and then it'll go on and react with another hand and link up the chains all along. And what are you doing back there?
I'm pouring it out so it doesn't smell bad. Now this material smells a little bit, so what we're going to do is, it takes a while for this stuff to set. So what we've done is we've put the money inside here. And what I'm going to do is I'm going to let it set over there in the hot plate, because it requires a slightly higher temperature to set. And then we'll give the $20 bill back. Thank you.
Okay, the next thing we're going to do is we're going to make nylon. And for making nylon, I'm going to need a couple of volunteers as well. How about you two right there? The two boys right there. Yeah, come on. See what you can do with that camera. That was going to
get out of the way.
No, it was going to be our.
Okay. Well, I'm sure they'll come get it. What are your names?
Nathan and Kyle.
So Nathan and Kyle.
Okay.
So what we're going to do is make nylon. And nylon is an interesting compound because the way it's made is from two molecules, two monomers, that are in different phases of an organic and a water solution. So what we have, I should explain a little bit about this. It's kind of hard to sort of explain all at once. Water and oil don't mix. Everybody knows that. And what we have here is a solution of something that is in water, and that's one component of the polymer. It's a monomer. And we have a solution of something that's in something similar to oil. It's called hexane. It's a hydrocarbon, for those of you who know what a hydrocarbon is. And this is another monomer. And what happens in this particular polymerization reaction is that one molecule in water hooks up with a molecule in the oil phase, let's say, and then it hooks up with another water molecule and another oil molecule, and the reaction actually occurs at the layer between the water and the oil. So what we'll do is we'll mix these two things together, and they'll form two layers, and between the two layers, that's where the polymer forms, and then we'll grab the polymer with the tweezers and roll it up on this graduated cylinder.
Why don't you come around this side?
Yeah, why don't you come around over here and you can see what's happening up there on the camera. Okay. So now here's what you want to do. Gordon, you want to take that one over there on the other side? Maybe we'll just focus on this one.
Good idea.
Okay. You're Kyle? No, you're
Nathan.
Nathan. Why don't you go with Gordon? It's scary, but go ahead. All right. So here's what we're going to do. So we mix the two, and you can see that there are two layers. There's the brown layer on top and the clear layer on the bottom. And the brown is the oil-like layer, and the clear is the water. And we're going to grab, and you can see that there's a string coming up. Okay, Nathan, why don't you, Kyle, sorry, whoever. Why don't you roll? Okay. why don't you roll this, and you can extrude some nylon.
I gotta get some tweezers. Throw me some tweezers.
No, this one you can't keep because it's kind of smelly. It's got some not so pleasant chemicals in it. So what you can see now, what you can see is that there's this thick string here, and the faster you roll this, the thinner the string is going to be. And so when DuPont or whoever makes nylon, they control first of all, they control the monomers, they control the rate at which this spins. Keep spinning.
Oh, wait, it's not nothing hard.
And they separate it apart so that they don't touch each other and they get nice, clean, dry
Okay, go ahead.
nylon.
Can you see this? Can you see the string coming right out of the solution? So that's coming out at the interface between the two solutions. That's where the reaction is occurring, and then we can just reel it out on these little cylinders. Okay? And actually, he could probably go for, I don't know, 40 or 50 feet. You can see over here that there's getting to be quite a bit of thread.
And so from this little solution, you can make a really long, continuous string of nylon. How long do I do this? That's really good.
Okay.
Okay.
Thank you very much, Kyle.
Thanks.
And what was the other name?
Nathan. Thanks, Kyle. Nathan.
Thanks, Kyle. Thanks,
Thank you very
Nathan.
Might want to take off the gloves.
Pick up the bottle. Thank you.
Oh, okay. He threw it a little too hard, huh? That's okay.
Okay, now we're going to show you how chemists have water gun fights. How chemists
We should spread this out a little bit.
have water gun fights.
And for this, we need to clean up the area a little bit here. What we have is a polymer called nitrocellulose. How many of you know what nitrocellulose is? How many of you seen a movie called Cinema Paradiso? Nitrocellulose is, sorry. Yes, buddy. Nitrocellulose is a material that is very flammable. It tends to explode when you burn it. And in the olden days, before we had these wonderful new polymers, people used to use nitrocellulose for movie film. And this movie, Cinema Paradiso, is semi-autobiographical. It's an Italian film. There was a fellow that ran the movie projector in the director's hometown. And when he was a young man, this older man that ran the movie projector had an accident where the film caught on fire and burned his eyes and basically blinded him. So you wouldn't want to use this particular polymer for that application necessarily. It's not the best thing in the world to do. Let's get it away from here.
The other thing that this stuff doubles for is smokeless gunpowder. Cellulose is a polymer of
Hey, what's up
starch.
with this? This my gun?
Yeah, that's your gun.
Is it
but
working? Why do I get a little gun?
It's not how big your gun is, it's how you use it.
Oh, okay.
All right, so the far plate is my plate, and the near plate is Professor Sammakia's plate. And we've set these two samples up with a little bit of phosphorus pentoxide on it, which, when it gets wet, will get hot, and it should be hot enough to make the nitrocellulose, or gun cotton, ignite.
Can we dim the lights a little bit?
Okay, one more time.
Okay, good.
We made.
No, that's too much.
That's a little too dark.
That's too dark. That's good.
All right, so we made. What? The crowd up here is complaining because they're getting wet. No, nobody squirted you.
Okay. So on the count of three, we're going to have a water fight, and we're going to see who can light their nitrocellulose first.
Okay, so it's a piece of nitrocellulose, which is very flammable, and we put a chemical on there which gets hot when it gets wet. Okay, so that whoever wins, the other person's piece of cotton will light first.
So which one is mine? The one closer to you?
Yeah.
I don't think so. That was mine. That
Okay.
was yours. Ready?
All right.
Go.
Oh. Dud.
Oh, it says you.
There we go. Hey, I heard that. All right, what's next on our...
Gels. Slide your gels over.
Which else?
Okay, so now we're going to talk about gels. And the show's about polymers, foams, and gels. And we're going to talk about gels a little bit and describe to you some of the things you can do with gels. And the first question is, what exactly is a gel? I think everybody knows what a gel is, but it's hard to define.
We've got a couple samples here of polymethyl methacrylate polyacrylamide gels that I'm going to pass around. They look like gigantic eyeballs. We got 7-Up eyeball and a Coke eyeball. And what I did was I made these inside a Christmas ornament, and then I broke off all the Christmas ornament like an eggshell. And what we have here is something that looks like finger jello, except that it's a little stiffer and you can't eat it. But we think they're pretty cool, so I'll just pass these around and you can take a look at them. Okay? These are examples of gels.
Or do you want to put one on the other side of the room?
Oh, well, let them compare. It's okay, it'll make its way around. Okay,
Okay, so
father-daughter.
what we need now is a father-daughter combination. We'd like somebody here, the father here with their daughter. How about somebody in the back of the room? We picked a lot on the front of the room. Anybody in the back with a, yeah, there you go. How about you two? Excellent. Can I have my wife's prop back? You don't want it anymore. Thank you. That's okay, you can keep those.
Okay, names.
What are your names?
Walter.
Kelly.
Walter and Kelly. Why don't you go in the front
Walter
there
and
so
Kelly,
everybody can
come
see
on
you.
down. Okay, there you go, Kelly. Here you go, Walter. Take the stoppers out. Turn around, face the audience. Here's what we're going to do. We're going to pour an equal volume of highly toxic, corrosive, we're going to pour some water that we put a little blue food coloring into. Okay, into these flasks, and then we're going to have another strength competition. Okay, and all you have to do is shake the flasks, and if you shake them hard enough, something good will happen, and then what you should do is turn the flask upside down and hold it on top of your head.
Wait, the stoppers. Where are the stoppers? Oh, there they are.
Okay, so here we go. Okay. Oops, excuse me.
Now, why don't you put your hand over that so it doesn't spill?
We have a stopper.
So now you got to shake really hard for this to work. Why don't you spread apart so your dad doesn't hit you in the head? I'm sure he's going to. Okay, so now hold on to it really good and shake really hard. Keep shaking. Keep shaking. Now the harder you shake, and as soon as you shake really, really hard, it'll all gel up, and you'll just have gel. Okay.
But you have to be strong.
So now when I count to 3, we're going to take the stopper off, and you're going to put it on top of your head. You trust me? You trust me? Sure. What's your name again?
Not shaking hard enough,
Shake
Dad.
harder, Dad. All right. Okay, so 1. It's just water, no big deal, right? It won't hurt you. No, don't do it. So why don't you turn, what's your name again?
Kelly.
Kelly, why don't you turn yours upside down and let's see what happens. Hey.
Ah!
Okay, so now
Thank you, Kelly. Thank you, Walter.
what we want to do is so what would this be useful for? What could you imagine? This is a polymer and a gel at the same time. It's a polymer that swells with water and forms a gel. What do you think it'd be useful for? How about a diaper? Something far more valuable if you have children. Here what we have is a diaper, and the material in the diaper is exactly the same material that's in that gel. It's a polyacrylamide gel substance, and when I spilled this last time, I got in so much trouble. And when you have some of this, you can put in the diaper, and it'll soak it up. Let's see. That's a lot of stuff. Let's see if it all fit in this little diaper. You don't think so? How much you want to bet? It takes a while for it to, it's all set. It's not bad.
Hey, save it for the diaper.
So it's an awful big baby, so we'll just So the point is, in the course of a night, you might have this kind of a problem. And what would happen is, well, not you. And basically, it soaks it all up. And it keeps it away from the baby. And we'll stop here. That's you! Oh, Gordon! Oh, Gordon, this is gross. What? Oh, man.
Sorry.
Jeez. I don't want this.
You might recognize this gel in a recent movie. It was one of the co-stars. Flubber. All right, we're going to make a little flubber. So we need more volunteers. Tarek, can you pick out some people?
Sure. 4?
Yeah.
Again, we'll go to the back of the audience so that we... Oh, we got everybody in the front. How about on the other side? How about you two? You and you. And you two. Go ahead and go down. What's your name?
Brian.
Brian, and you are? Jermaine. You got 4.
Names?
Brian or Jermaine?
Brian.
Brian, Jermaine,
Jessica.
Jessica, Christy. We're going to forget those. That's all right.
It's Trummy.
Actually, for this one, we don't. Let's completely safe.
All right, turn around. Okay, stand next to one of these beakers. Okay, and what you're going to do, well, let me equip you with the stirring stick. Now, don't hold the stirring stick right at the end because it is a little fragile. Sort of hold it somewhere in the middle as you stir. Okay, there you go, there you go, there you go. All right, now for the contents of the small beaker, and if you can, step to the side a little so or hold it in front of you so everyone can see what you're doing. Pour the contents of the small beaker into the big beaker. Right, the small. Oh, you're too far over. Slide down. You come all the way down to this end. Here we go.
Okay, so let me explain what's going to happen here. What we have are 2 beakers, one of which contains a polymer that's already in place. And the other beaker is something known as a cross-linking agent. So if you imagine
Go
a
ahead and start
polymer
stirring.
is a long chain, and there's a bunch of these long chains in there, a cross-linking agent
Do you like blue?
cross-links between the 2 chains and forms a bond from one chain to the other. So now, whereas before you had a bunch of really long chains, now you have all the chains tied to each other and cross-linked, and now the properties of this huge aggregate molecule now are different from the properties of the original long chain. The original long chain molecule we had was dissolved in water. It was free-flowing. It flowed out normally.
Turn around and stir. And
Once we cross-link them and join them all together, they now don't become so free-flowing anymore because the chains can't move relative to each other, and they become one giant molecule effectively with water embedded inside them.
Turn back this way.
And what ends up happening is they become these gels.
How's that working? It's setting up? Okay. Keep going. Okay, now the one thing we're going to let you take these home. The one thing I have to warn you though is that I just put food coloring in it, so you don't want to touch it to your clothes because it will stain your clothes.
I don't want to sneeze on somebody with them. It's not right.
Oh, it's getting there. Here we go. Okay, tell you what. Why don't you can take these back to your seats.
Well, you want to show them to the cameras to compare the consistency? Well, I'll just show them with this thing. That's fine.
Okay, take them back to your seats, and then at the end of the show, we'll give you a Ziploc bag. And believe me, it'll end up looking like snot when it's all done. Welcome.
Where's the P205? Is that covered? You want to see that?
Huh?
The P205?
Is it covered? Yeah, I'm sure I covered it. What's next?
Smart Johnson.
Oh, okay.
Oh, we got a cold one and a hot one? Oh, let me check.
Okay. That's okay.
Okay, this,
You want to show that?
it's not done yet.
Okay.
It's still too hot.
Okay, what we'd like to show you next is something called a smart gel. And I'm going to need to use this camera, so
Oh, sorry, let me get this out of the way here.
we'll pass these around so everybody can take a better look. These were invented fairly recently by a professor, Toyo Tanaka at MIT, and he was kind enough to share some of this with us. Okay? So normally when you take a gel or any fluid and warm it up, it gets thinner in consistency, right? If you take motor oil and you heat it up, it gets thinner. Well, what he discovered is a compound, a gel, which when you heat it up, actually gets thicker. Okay, so let's see if we can. No, that's not so good. Where are we here? Okay. You can see that there's a little steel ball bearing in this, and you can see it going up and down the tube because this tube is right now at room temperature. Okay? Now I'm going to take an identical tube, okay, that also has a ball bearing in it, and the ball bearing also moves up and down. Okay? And I'm going to put it in this warm water briefly. And I'll pass these around, and so you can take a closer look at them. So I'm putting it in warm water, but when you get a chance to touch it, you'll see that it doesn't actually, now, let's see, where are we? Okay, now you can see that ball bearing is stuck at the top. Okay, so again, normally when you heat up something, it becomes thinner in consistency or less viscous, whereas this material is unusual because when you warm it up, it actually becomes more viscous. Okay, so what is this being used for? The company called Gel Sciences is marketing it as an insert for an inline skate boot. Okay? The idea is it's a gel at room temperature, it's liquidy, you put your foot into the boot, okay? Then it warms to your body temperature, and it gets thicker, and that way you get the absolute perfect fit on your boot. Okay? So I'll pass these around, and it'll be pretty obvious which one's the hot one, because the hot one will be all gelled, and the cool one won't be gelled. And we'll start that on this side. Okay?
Okay. You know what? We need to clear off some of the stuff over here because we're going to do the soap bubbles next. Or do you want to do styrofoam head first? Why don't I do styrofoam head while you clean up?
Okay, great. Well, let's talk about what a foam is.
Okay. Oh, okay.
Okay, now we'd like to turn your attention to foams. And the key thing about foams is that foams are materials that contain lots of trapped gas in the form of bubbles. Okay? Lots of trapped gas in the form of bubbles.
So can someone name one compound that you might think of that would be a foam? There you go, styrofoam. So people talk about styrofoam as a disposal problem, as a landfill problem. But in fact, you can alleviate that problem if you realize that styrofoam is mostly air with a little bit of polystyrene polymer around it. And so one way to illustrate that is to take this styrofoam head and dissolve all the air bubbles out of it. Get rid of all the air bubbles. And we're going to do that by dissolving the styrofoam in an organic solvent that dissolves the polystyrene, and then the air escapes. And you can see that this big thing here that pretty much takes up this entire vessel isn't really so much of a large object after all. So here we have a chemical called acetone, and it's commonly used in, or it used to be used in nail polish remover. It might still be used in nail polish remover. Is it?
Ethyl acetate.
Ethyl acetate also.
Mostly, yeah. That's
And I'm going to pour a little bit of this
I bet that's enough.
in there. What do you think of the makeup? Yeah, think so? Gordon did it. Okay. And we'll see what happens when I put this in there. Don't do drugs. So ordinarily when we do this, we have a smaller vessel, and I can sort of do all kinds of things with it. But you can see it's all dissolving, and the volume of the acetone isn't really increasing by that much. And you can see the little bubbles being given off, if we can get the camera on that, as she melts. I want to thank Jan Tyler for the makeup.
You have to, thank you.
So really, this huge styrofoam head is mostly air, as you can see, and only a little bit of material in it, a little bit of polystyrene. So the volume of the liquid hasn't increased that much. Okay.
All right, now we're going to do some more gratuitous burning things that only peripherally have something to do with foams. And that is, we're going to show you a demonstration with bubbles, the way chemists make bubbles.
Steve, could you give us a hand with that? Could you work the hydrogen, and if I tell you higher or lower, adjust the needle valve just a little bit so that we get the right. Thanks a lot. Okay. We want the lights dimmed a little bit for this also. Oh, that's a good idea. Yeah, why don't you, let's
Move it to the end of the table?
Yeah, move it to the end of the table. Lower. Lower, thanks. There we go. A little lower.
Am I going to need this? No?
No.
Okay.
Okay. So go ahead, fire it up.
What do I do with the lighter?
You want to not stand on the table?
No, I'll stand up there. Otherwise, I won't
Oh,
catch
wait.
up to it.
Okay. Let's get up gently.
That's okay. Okay, can
we
we
dim the
turn the
lights a
lights
little
down a little bit?
Can we dim the lights some more? Oh, it went out. Where's your lighter?
I got it. Hey, you're getting them too close to me.
Two more.
So what we're doing is we're making bubbles that are filled with hydrogen, and hydrogen is lighter than air, so they float. And then when we hit them with the candle flame,
Last one.
one more.
Okay. All right, two more.
Let's get it until we. Wah! Wah!
Shut it off.
All right. Okay, for our final trick this evening, we'd like to show you a demonstration called elephant snot. What we're going to do is we're going to make bubbles. In this case, we're going to make soap bubbles. So what I've got here is I've got some soap solution in a large cylinder. And the thing that's going to provide the gas is hydrogen peroxide. And some of you may have experienced hydrogen peroxide making a gas, making bubbles, because if you ever get a cut, sometimes you'll put hydrogen peroxide on that cut, and it turns out that your blood contains an ingredient that catalyzes the decomposition of hydrogen peroxide, makes bubbles. What we're going to use for that is we're going to use some potassium iodide, potassium iodide will cause the hydrogen peroxide to break down into O2, oxygen, and water. And then the oxygen and water, and then the oxygen is going to create bubbles in the soap, and we're going to make a huge amount of elephant snot. Okay, here we go. Everybody watching?
Tell you what. I don't want to put the glass in. I'll tell you what, let's do it in this cup right here. This will work right here. We should not drink out of this one. You know what, I'll do it. You get any ice on you? Any glass on you? Oh, you're all right. Okay. You cut yourself?
It's okay, it won't hurt it.
Here's the bottle bill. Okay, so I lost my mic. It's all right. Can you hear me in the back? So if you recall earlier in the show, we polymerized a $20 bill, and we took a liquid, added a little bit of initiator, and heated it up to polymerize it. And I didn't do this exactly, the correct way, because you should do this in a slow fashion. If you do it too fast, you get these little bubbles in the thing, and we only had about an hour to polymerize it. But what you can see is two things have happened that are both pretty remarkable. First of all, is that? Oh, okay. First of all, you can see that what used to be a liquid is now a solid. I broke the glass off the outside of the polymer there. And the second thing that happened that's really remarkable is that the $20 bill is now a $1 bill. I don't know how that happened. So somebody has a 20 somewhere. I don't know who it is. So anyway, so this is what happens when you make plexiglass. If you don't do it quite right, you get all these little bubbles. I'll pass this around the audience, and you can see, as I promised, you get your $20 bill back.
Okay, for our final trick, or final thing that we do, we usually at this time pass out a lemon meringue pie.
And then we pass out.
And the reason why we pass out a lemon meringue pie is because a lemon meringue pie very neatly summarizes the things that we've tried to tell you about. First of all, the crust of the pie contains starch, and starch is a polymer made up of sugars that nature makes. And then the lemon part is typically a gel. You typically make it with gelatin or something like that. And then the meringue, for those of you who don't know, meringue is egg white into which you blow a lot of bubbles. So sort of like elephant snot, you whip a lot of bubbles into it. Well, on a Tuesday afternoon in Newport News, you cannot find a lemon meringue pie. So I got what I like to eat. And we were going to keep it, but then somebody said if we got the pie, we ought to really give it away. So we always have trouble deciding who we're going to give the pie away. We ended up getting a banana cream pie. Banana cream pie. And it's still the case that the crust has starch in it. And that's a polymer. And the whipped cream is sort of a foam because it's got air beaten into it. And the way we like to give it away is if there's somebody in the audience whose birthday is today, but wait. There might be more than one, okay? So I'm a little worried that there might be more than one. So I want to give it to the youngest person, okay? The youngest person whose birthday is today. All right, and I'm going to ask for proof. And if I don't get proof someone's lying, I'm going to be really upset.
15. Who else?
We have a 15.
How old are you? 14. How long have you been 14? 5 years? Anybody else's birthday today? Are you really 14? Stand up. He's not. Are you really 14? Anybody vouch for this young man? All right.
All right, we have a 15-year-old.
So you get the pie. Happy birthday.
Happy birthday. Well, we've had a lot of fun being here tonight, doing our show for you. I hope you've also had some fun. If you have any questions that you'd like us to answer, we'd be happy to answer them if you'd like to come up. Okay, and I guess there's another show next month. I need to sign this. I see. Where do you need me to sign it?
Yeah. green thing that was being passed around?
That gave them credit for their ice
Right,
cream.
right. So what happened
If
is...
you're in need of signatures, please see a staff member outside the auditorium.